Okay, today we are starting our real study of the natural language processing. As we said before, we are going to start from the beginning. Böyle oturunca görebiliyor musun sen? Yoksa şöyle biraz daha ortaya mı alayım? We are going to do morphology. Before the morphology, I like to start. Remember what we said last time? Let me show you the last part of the introduction section. We said that, okay, we will, okay, we will follow this hierarchy of natural language processing. Phonology is not part of this course. It is about sounds and etc. Morphology is the study of the words, and we are going to look at this morphology very carefully. Then we are going to look at how these words come together. That's called syntax. Then we are going to look at the semantics, which is the meaning of the words. Meaning of the words sometimes doesn't make much sense if I don't give you the it's changing. If I don't give you the context of the words or the sentences, then this course is the social pragmatics. We talked about that. So we are going to, before we start looking at the words themselves, we said that that's what we're going for now. We said that what kind of tools are we going to use in NLP, models and algorithms, etc. We said that we will be using state machines, and we talked a little bit about it, rule-based approaches, and then with the algorithms we have dynamic programming. Today, on a simple, natural, I wouldn't say simple, maybe I shouldn't say simple, on our first introductory problem of NLP, which is the spelling correction. Yes? Yes, I did. Yes, thank you. So we are going to look at this spelling correction algorithm, and we are going to look at these two paradigms, state space search and dynamic programming, and you will understand what we mean by those. And we will come to state space search and dynamic programming in a number of cases, and that's why on a simple example you will have your solid idea, and I am hoping that it would be useful. So let's look at this edit distance thing. So edit distance is very, it is defined in a standard way. Suppose somebody typed this word using the keyboard, graph. It doesn't mean anything in English. It is not in the dictionary. So that must be a spelling error, right? I didn't write it. I didn't type it correctly. It is either graph, graphed, grail, giraffe, and etc. Okay? I don't know which one it is. It could be any of them. So the common solution to this problem, is if somebody made a mistake, probably it is one or two keystrokes, okay? So let's try to find the distance between these valid words and this one in terms of number of keystrokes necessary to change this one to this one. To change this one to this one, we need to add the two words. So this is the two letters, right? So if I add F and E, just two keystrokes, right? How about this one? What is the distance between this graph and graph, whatever it is? I guess it is. I need to replace this T with an F, then delete E, right? So replacing is maybe 2 keystrokes, delete and add. Maybe replacing is just 1 keystroke, I don't know. Let's make it 2 again. Grail to graph is going to be, what is the, I think I need to add these 2 and remove those 3, it's 5. Giraffe and graph, it is, I need to insert an I, that's 1. It's like 1, right? Is that correct? Yeah, I think G, if I insert an I between G and R, yeah, that would be 1.
Can I ask about the third word? I mean, why didn't we replace it?
Third word?
Yes. We could replace the letters instead of deleting and then adding. Maybe it could.
Well, in this case, I am assuming that replacement and deletion and insertion are the same cost. They are all 1. So as we are going to see, there are multiple ways of changing this word into this word. As long as their costs are the same and result is the same, we can take one of them.
But it could be 3 too, right?
Yeah. Which one?
Third one.
Third one. So you are saying that what should I do?
Instead of deleting the letters, we can replace them.
Oh, okay, yeah, okay. Let's do that then. So let's replace I with F and L with F. That's 2, and erase E. Then that's going to be 3. Yeah. So this is better. Okay. In that case, it changes. So this is, if I measure the distance between these 2 words, okay, editing distance, I can say that maybe this is the word that the user is trying to, user of the word processing package is trying to write, okay? Because that's the shortest one. I don't expect that people are making lots of mistakes when they are writing words. I mean, one letter mistake, maybe 2 letter mistake, and choose one of them. That's one thing. Spelling correction, we can use this edit distance. You might say that, where did you get these words? I don't know. I mean, we are going to look at that problem later. Where do we get the candidate words? Okay. For now, you may say that I am going to get the whole dictionary with 100,000 words, and I'm going to measure the distance between all these words with this one. Okay. So it has to be fast. By the way, I did not give you any algorithm to find the shortest or the smallest edit distance between these 2 or that. We just did it by ourselves, but it is not a very easy problem because, as I said before, or as Sibel pointed out, why don't we do this and this and it will be shorter? The most trivial algorithm between these 2, connecting this one with this one, is remove everything out, okay? Take everything out. 1, 2, 3, okay, 6 deletions and 4 insertions. At a cost of 10, I can do this correction, right? So remove everything, delete everything, and type everything. This is an algorithm to do it, but this surely doesn't produce the minimum edit distance between these 2. So how do I find the minimum edit distance between these 2 words? That's the question. Yes.
That's not logical because deletion and replacing is very different, I think. Because let's think to the very different 2 words. For example, water and I don't know, iPhone. So just type, right? Between space, but it's we can't say these are similar. It's just 5, but it's not similar. So I think replacing caused us to.
Okay. When we look at the final algorithm, we will consider that too. Okay.
I think it's not logical.
Well, why not? Because sometimes I do this, right? Replacement is sometimes just one keystroke. Let me open this. Where is my insert? Can I find a... If I can find the insert stuff, remember, instead of writing insert, instead of write overwrite, usually on our keyboards we have the overwrite available. When you do that, okay, if you ask that question, then I am going to do, okay. So these are my words, words, okay. Let me make this a little bit, or maybe I should do it that way and make it, okay. So to make, let's say this is, okay. So to make this to a word or words, you are saying that I should delete one and insert one, that the cost of it is 2. But if I do this overwrite thing, I don't know whether do you guys know how to write the overwrite thing? Do you know that, right? Usually overwrite is somewhere, yeah, it is here. With the function, am I overwriting now? No. Insert, where is insert? Is this one insert? What? 0? Who is talking? Who is talking? What?
If you want to insert, it's numlock and 0.
I don't have numlock. I don't have numlock. This is not a full.
We may just select the letter and overwrite.
But that's again two strokes. But you understand what I am saying, right? I mean, if you switch to the overwrite mode, then whatever you will type is okay. Let's do it. Okay. I am in the overwrite mode, right? Overwrite mode. Whatever I am typing is replacing the other letters. So in some cases, it could be just one keystroke. But if it is not, then we can take this into the account too. Okay. For now, I'm just for the simplicity, I'm just assuming it is cost is just 1. Okay, this is one example. Another case where we are using this edit distance is there's computational biology people, they love this a lot. They say that giving 2 DNA sequences of 2 different samples, I don't know, the sample one is from a control subject, and sample 2 is something that I took right now, and I like to register these 2 sequences together. I see that these are not the same. One thing you would say that, okay, these are not the same, but I don't want to do that. I like to find the best overlap between these 2. It looks like if I do this insertion here and insertion there, these 2, right? And these 2 and this one, this is, I think these are replacements, right? Just replace it. Okay, maybe why don't I do it this way? Yeah. Insert one to the second sequence. Okay, delete one from the first sequence. Insert and delete. Replace. Insert and delete. Replace, etc. If I can find this this mapping between these 2 sequences, okay, and I am saying that I am going to give you an algorithm that will find this correspondence between these 2 sequences, and I am going to guarantee that you cannot do better than that, okay? So this is 1, 2, 1, 2, 4, 5, 7, 8, 10, and 13. With a cost of 13, okay, with a cost of 13, you can register these 2 sequences together, and 13 is going to give you how different these 2 sequences are. Also, this map will give you how to change from one to the other one, okay? So it looks like there is a very nice overlap around here. This kind of stuff would be very useful. So computational biology people use this algorithm, this edit distance, a lot. Other than that, we are going to use this in machine translation, information extraction, speech recognition, and etc. So this edit distance is used in many places as long as you have one-dimensional data, okay? As long as you have one-dimensional data, you can measure the edit distance between two sequences using the algorithms that I am going to give you today. And the best algorithm I am going to give you today is the dynamic programming algorithm. That's why it's going to be a very nice introduction to edit distance. Okay? So the minimum edit distance between two strings, once we solve this problem, we can apply it to many places. Okay? So what is the minimum number of editing operations? We have three operations: insertion, deletion, replacement, or substitution. Okay? The cost of each of them could be 1, 1, 1 or 1, 1, 2. Okay? Or sometimes it depends. I mean, substituting U and Y could be something cheaper. Why? Because U and Y are very close by on my keyboard, right? It is very common to press the Y key instead of U key because they are very close to each other on my keyboard, etc. So the cost of insertion or deletion or substitution could be very different depending on your application, like your question. Okay. Okay, so I like to an example. I like to find the distance between intention and execution. Okay, and I guess this is the best alignment. It looks like I am going to delete this one. Okay, delete this one, substitute, okay, and keep this one, insert a C, substitute, rest of them is the same. So the total cost between them is 5. If substitution costs 2, so delete and insert, then that cost is going to be 8. So this guy Levenstein, his method says that substitution costs 2, and the algorithm that we are going to give you today, the dynamic programming based, is due to this guy. Okay? We talked about this, computational biology, they use edit distance a lot. Okay? Interesting example here. What did we say last time? Machine translation is one of the major applications of natural language processing. And we said that it's a typical AI problem. Since it's a typical AI problem, we don't know the definite answer. We don't know the best translation of a Turkish sentence, right? Let's say I gave you a Turkish sentence, okay? Sözcü üst düzey hükümet danışmanının vurulduğunu teyit etti. And I translated to English. I translated to English this way, okay? Our new machine translation system translated it to English this way. Can you say which one is better? We can't, okay? But I can. So how am I going to measure my success? How am I going to measure my success? I mean, it is not exactly the same way that I translated it. One of them says spokesman confirms senior government advisor was shot. The other one says said the senior advisor was shot. They both look like nice English sentences. So what am I going to do? Some people say that let's measure the edit distance between them. This is the same. Keep it. Okay, substitute it. I can substitute confirms with said. Why? Because they are almost the same thing. Okay. The article stuff, determiners, sometimes we use them, sometimes we don't. Okay. I just replaced it. I just inserted it. I kept it. I deleted this one, and the rest of them is the same. So the distance between these two is kind of 3 if you like to measure it that way. If I need to replace everything with the other sentence, that means that these two sentences are very, very different. Okay? And maybe I can assign stuff like, maybe I can freely insert this and a's anywhere I like. Maybe I can do this kind of substitutions. They are, if I look at the meaning of the two words in the dictionary, they are kind of the same. I can substitute them in a very cheaply. Substitution between these two is cheap. But if I am substituting two words that are very, very different in terms of meaning, then its cost is going to be high, etc. Okay? Another one is named entity extraction. Remember the named entity extraction, named entity recognition. Given a sentence, we like to find the persons, companies, dates, places, etc. inside those sentences. Okay? So running the edit distance between these two phrases, IBM Incorporated or IBM, okay, is going to help us. Maybe you're going to say, okay, both of them are the same. So if this is my ground truth, if I am extracting this, okay, then I am kind of okay. Or the Stanford University John, Stanford University President John, they are the same entities. That's what I am trying to say. Okay? So edit distance is not limited to this kind of stuff. That's what I am going to say. It's not about just letters. Depending on your alphabet, in this case, my alphabet is the words themselves, then I can use it in many other places. As long as your data is sequential and one-dimensional, we can use this minimum edit distance algorithm anywhere you like. Okay? Good. Let's say, I mean, this is no different than numbers, right? If you have a bunch of numbers like, how can I, yeah, it rained and rained and rained and it is sunny, sunny, sunny, cloudy, cloudy, rain, sunny, cloudy. This happened in June of 2020. And I like to find the most similar weather pattern in the last 100 years in June. Okay? Get all of them, all these weather patterns for the last 100 years, and find the one that is most similar. You're not going to find exactly the same thing, right? It's not going to be exact, but your dynamic programming algorithm is going to tell you, okay, this is the most similar one. If you substitute these days with the others, and you will get the most similar one, etc. Okay? So as long as your data is one-dimensional and sequential, then think about minimum edit distance, whatever you are researching for. Okay? So the first thing, usually AI people, they start with the most stupid algorithm that they can apply. We are going to pose this problem as a state space search. Okay? We are going to apply this problem as a state space search. Remember the state space search? The last time I gave you the example was 8 puzzle game, right? I can move the tiles around, up, left, right, and do this with all the possibilities. Do your search until you find your solution. Okay? That's what we did. I guess it was, yeah, it was this one, right? So in this case, there are 2 possibilities. So my tree branched in 2 ways. Then I have 3 possibilities, and continue until you find the solution somewhere in the space. And remember, the space was very, very large. The size of this space was 9 factorial, remember? And we are going to run something like that, okay? We are going to do something like that. What was our goal? Starting from intention, I like to find the distance to execution, right? That was it, the execution? Yeah, execution. So starting from intention, with the first letter, what can I do? I can delete it, okay? I can insert a letter from my target word, which is execution, the first letter is E, or I can do the substitution. Okay? I don't know which way to go, so I am going to continue with this one. There are three possibilities. I can delete N. I can replace N with what? I can replace N with not E, no. I replace, oh, yeah, well, yeah, I can, that's true. I can replace N with E because that's the execution, or I can substitute N with E. I can go it that way, okay? And I can do the same thing. What can I do now here? I can delete I. I am in the second letter now, right? I can delete I, or I can insert an X in there because I already inserted E, right? Or I can substitute I with an X. Okay? Okay? So if I continue this way, and if I do a breadth first search, let me breadth first search. I'm going this way, okay? The first time I see my solution, then I'm going to say that, okay, this is the shortest path from the root to the end. So what is the size of this? What is the size of this tree? How many entries do I have? What? Who's talking? You are saying infinite? No. Because at every step, I am either deleting, inserting, or substituting something. If I keep deleting, this word will end. If I keep substituting, what is the substitution, the total substitution length? It could be the maximum of the letters, either of the intention or execution. And insertion is going to be, so I think the depth of this tree, it starts with intention, and it goes like that. Depth of the tree is going to be what? No, it is not 9. It is 1, 2, 3, 4, 5, 6, 7, 8, 9 plus how many letters in execution? 9, right? Is it 9? Yeah. 18. Why? Because remember, if I keep deleting everything, this will be done. Then I will have to insert everything, right? So the worst editing I can do is deleting intention and typing execution, right? That's 18 keystrokes, okay? So the depth of this, maximum depth of this tree is 18. So how many nodes maximum can there be at a tree like this if the branching factor is 3?
3 to the power of 18.
Yeah, 3 to the power 18. And this is a very, very large number. I don't like this number, right?
But some branches may end early.
Yeah, well, I mean, we are talking about upper bound. Okay, we are talking about the upper bound. I mean, you will never know. You will never know. I mean, let's say if my word is A, B, C, D, I like to find the distance to X, Y, Z, K. In this case, I am going to do 4 deletions and 4 insertions. I mean, I have to explore the whole tree, right? So this is a very large number. I don't like this number. Can I do better than that? That's what we are going to do. Can I do better than that? Okay. State space search. We use state space search, but we don't do that in a way like this. Okay. We do it in a more smarter way, more intelligent way. And to do that, we need to have some kind of heuristic rules, but I'm not going to talk much about them, okay? So we can't afford to navigate naively. this is too expensive. Okay. By the way, remember what I said? Delete all the letters and insert all of them, or insert all the letters and delete the remaining ones. I end up at the same position, right? There are lots of redundant branches of this tree. Okay, we don't like to do redundant stuff. That's the waste of time and the memory space. Okay, lots of distinct paths wind up at the same state. Okay, and we don't care how many times we solve the same problem. We don't have to keep track of all of them. So we are trying to find the shortest pattern, etc. Let's find a solution for that. Okay. So we are going to give you this algorithm. This is called Minimated distance algorithm. We have two strings, one of size n, the other one of size m, and we have a two-dimensional table, dij. Okay. dij, each element of this dij keeps the distance between this string and this string. Okay, this string and this string. Remember what I said? X has a length of n, y has a length of m. If I like to find the distance between the first letters of these two strings, then you need to look at this element inside. Sorry. You need to look at the element of this table, D11. D11 will give you the distance between the first elements of these two strings. Okay? And D22 will give you the distance between the first two elements of that string. Let's try to do that actually. Remember our example, execution EX, and let me try to write it this way. Okay, this is 0 and 0 with why can't I let me draw it better. Okay, 3 by 3 EX. What was the second one? Intention? Well, it's not a good idea, but let's say, okay, this is intention. This is 0, 0. It means what? Edit distance between two null strings. Okay, this is 0, 0. Edit distance between two null strings. How about this one? What does this mean? I am trying to convert this to this. Okay. So this is the edit distance between two null string. What does this box represent? It represents the edit distance between a null string and the string of E. How do you convert a null string to an E? I make an insertion. The cost of insertion is 1. Okay. What is this? This is the edit distance between the string I and the null string. So how do you convert I to a null string? I just delete it. That's the cost of it, right? 1. How do you find the edit distance between I and E? How do I convert I to E? Okay. I would delete I and insert E, right? So 2. This is 2. So this little box here, okay, this little box here solve the subproblem of edit distance between I and E. Well, you might say that you don't need to be a scientist to solve this problem. I already knew that, but this is the basics of the algorithm. And the dynamic programming, you know from this, I mean, those of you who took the algorithms course, dynamic programming is also, it says that I am using the principle of optimality, okay? If a problem is solved, and if that problem is my sub-problem, then I don't have to solve that problem over and over again, okay? I don't have to solve that problem over and over again. I use that solution. So if I know how to find the edit distance INE, then remember we are trying to find the distance between intention and execution. I already solved the problem between these two letters. Maybe if I solve the rest of it, I can combine it with this one. Let's try to make it bigger, a little bit bigger. So how do you match a null string with EX? Okay, I already solved the problem of matching a null string with E. All I am going to do is add 1 to this number and make it 2, right? Use blue maybe. So that's the solution to edit distance between a null string and EX. Do the same thing here. How do you reduce this word in to a null string? I already did this. I am going to add 1 to it. It is just 2. Okay? It is like 2. Let's look at this. Let's look at this box. Okay? This box says that how do you find the edit distance between in and E? Okay? In and E. So what are we going to do? I already found the distance between I and E. It was 2, right? I and E, it was 2. But in this case, I need to delete one more letter. So one more keystroke. It is going to be 3. Or I can come from this path. I already know how to reduce in to a null string. If I add a character E to that one, it's going to be 3, right? Okay. Similarly, so I can do it both ways. I can either go from this way or that way. Or if I like, I can go this way too. What is the meaning of this one? This one says that, okay, I know how to reduce this I to a null string. And if I replace n with an E, and the cost of the replacement is 2, then I can get a 3 here, right? Continuing this way, okay, what am I going to write here? It is again 3, and I can come to this place in three different ways, either here, or there. And this one is going to be what? This one is going to be 4. So it looks like I solved this problem. The edit distance between in and x is 4. You cannot do better than that. If insertions and deletions are cost of 1 and substitutions are 2, then this is the whole thing. You might say that I could have done the same thing. I could have done the same thing with the state space search, but with the state space search again, our state space complex is going to be 4 to the power 3, and it is what? 16 times 16. I don't know what it is, like what it is. 256. Yeah, 256. If you do it the most stupid way, this is the upper bound, and we are talking about 9 numbers here. Okay, this one is talking about more than 200 numbers. Of course, this one is better. So let's generalize this idea again. Remember what we are trying to do. This table, Dij, it keeps, okay, the minimum edit distances between this string and this string. The first I letters of x and first j letters of x. And I only filled the beginning part of this table. And you kind of understood how we are going to expand this. This is what I am going to do actually. Let me erase this part that we have. I have, okay. Okay. Intention to execution. Null string, okay, null string. I know this is 0. The edit distance between two null strings are 0. And by default, without making any calculations, I can write this 0 to 9 and 0 to 9. By coincidence, by pure luck, this intentional execution has both 9 letters, okay? They don't have to be equal size. So I put 1, 2, 3. So what is the meaning of this 9? How do you, what is the minimum edit distance between a null string and execution? Well, I know I need to insert 9 characters. Or what is the edit distance between this intention and a null string? You need to delete 9 characters, right? I know this. Okay? So let's continue filling in this table. This one, I can do 3 things. I can either delete I, okay, when I come this way. What am I going to do? I am doing, if I do it this way, what is this? This one says that I have deleted I, and I can now insert an E. Delete 1, okay, insert E is 2, or I can do the same thing here. What does mean? 1 means I made an E out of null string, okay, then to go to that, I am deleting this I, it is 2, or I can directly come from here. I am directly replacing I with an E. All 3 paths are possible and they are the same. They are the same cost. Okay, let's continue. Let's continue, and I'm trying to reach to some interesting position now. Okay, this one is going to be 3, right? How do you find the edit distance between I and EX? And this one is going to be 3 again. And this one is going to be 4. And if I continue this way, when we hit, see this one? When we hit this one, there will be interesting stuff happening. Let's head for that place. T and E is going to be 4, and this is going to be 5, right? Okay, how about this one? This is going to be 4, right? This is going to be 5. This is going to be 6. And how about this one? 5, 6, right? Let's look at this. Okay, so it looks like I am doing this. Okay, this is the problem I am solving. That's what the dynamic programming does. It ignores the rest. I am just looking at this problem. How do you find the edit distance between int A to Gebze? Okay. If I delete, okay, if I delete this E, I can come to this place and it would be a 7. If I insert an E, I would come to this place and it would be a 7. But if I do this replacement, the cost of this replacement will be 0. Why? Because I am replacing E with an E. I don't have to do anything. So this is going to be just 5. Okay? So if I follow this path, this guy, and to come to this place, I will have either this place or this, doesn't matter. But I will definitely follow this path, and it's going to be 5. Okay? So this definitely solves the problem of finding the edit distance between this word and, if I use 4 fingers, yeah, no, bad. Okay, I'm going to use 2 fingers again. This word and this word. Okay. If I continue, and you get the idea, right? You get the idea. Let's try to fill this in. It's going to be a lot of work. So I guess this is going to be 5, 5, and this is 6, and this is 7. Here is going to be what? If I do the replacement, 6, right? So the replacements are the ones that are replacement with the same letter are the ones that are going to. What is the cost of this one? What should I write in here? Previously, I kept adding one to the one before, right? How about this one? What is the cost of? So what should I ask? What is the question? What is the cost of? What is the cost of replacing the word I with execute T, right? So that's 6. If I include this O in here, I cannot do this deletion. This is expensive because this is going to be 9. Okay. I cannot the replacement I and O, well, it's going to be 9 again. But if I come from here, just one deletion of I is going to be 7. And then 9. Sorry. And then 8. Okay. Let's do this. This is going to be 6, 7. Oh. Did I make a mistake here? This is a mistake, right?
Yes.
Yeah, well, there is a mistake. Yeah, it should have been 3, right? Nobody told me that. Okay. So I solved this problem maybe wrong. Well, in this case, this is going to be different. Let's solve it again. Because if I go this way, going up means what? Going up means delete this letter, right? Going right means insert this letter. Going up is 5, going right is 5, but if I go this way, it is free because I am replacing it, so it is going to be 3. Okay? Since this is 3, all of my calculations were wrong. Here, let's delete these arrows. Okay. How about this now? If I come from here, it's going to be 6. Deletion. Replacement is going to be 6. But if I come here, it's going to be 4. Right? Now let's look at this problem. If I come up, that is insertion is going to be 7. If I come from this way, it's going to be 5. And if I come from this way, it's going to be 5. So the cost is 5. Well, final result turns out to be the same. It is 5. But that means what? I can come from either this way or that way. Yeah.
So why is replacing is free?
Well, I mean, replacing E with an E is free because I am not replacing anything. I am keeping that word. I am keeping that letter. I am not overwriting it. I am not deleting and inserting it, right? What is the edit distance between A, B, C and A, B, C? You tell me. 0. Why? Because I am not replacing anything. I am replacing AM with an A, B with an B, C and C. What is the cost of replacing C with a C? It is 0. What is the edit distance between ABC and ABD? It is just 2. Replacement cost is 0, replacement cost is 0, and replacement cost is 2.
Because delete.
What?
Because delete D after insert.
You could do it that way, delete D and insert C, or insert C, delete D, or just directly substitute it, okay? Remember, we have 3 ways of doing it, okay? If we are going this way, that means we are inserting it. If we are going this way, deleting it. This way, it is substitution, okay? Good, yeah.
I understood the increasing but can I speak Turkish?
No.
I understood this it's increasing but why it's increasing? Why it's increasing?
You understood? What? You understood what part?
Replacing E with E doesn't cost anything. I understood this stable but why it's increasing?
Nothing is decreasing.
From 4
Well, no. It is 4 to 5, it is increasing. This one is keeping the same, right? This one is same. This one increases one more. Why wouldn't you expect to have a larger cost at the upper right corner? Because that's a more expensive box. I mean, this is cheapest. The edit distance between null string and null string. And this is the edit distance between this 4-letter word and this 3-letter word. I think I didn't understand your question right. Say it again.
Onun E4 ya. Can I speak?
No, you can't speak in it. Okay, this is 4.
But why
It is not, I mean, you are saying it is increased, it decreases from 5 to 4. We don't follow this path, okay? If you follow this path, it's going to be 6. Okay? We either follow this path or this path. Okay? So we don't choose to delete an E after we got to EX, okay? We delete one more character or we replace E with an E.
We are just selecting the minimum.
Sure, yeah. We have 3 alternatives. We choose the minimum. And we do it all the time. So at every box, we have these 3 options. And we have total of 9 times 9 boxes. That means what? 9 times 9 times 3. That's the total cost. This is 81 times, so total of 240 decisions that we are making. Okay? Instead of 3 to the power 18, which is a very large number. Okay? So keep doing this. Let's keep doing a little bit more. This is going to be, I guess, what, okay, tell me what this is. What is this? By the way, to calculate this one, all I need is this one, and this one. I need to look at only these 3. Okay? So I can come from here to there. It is going to be 6. From 3 to there, it's going to be 4. 4, maybe, well, I need that number. If it is the same thing, then it's 4, other it is different. So it's going to be 4, right? So this one says 4, this one says 6, and this one says 6 too.
Sorry, I have a question. Substitute means for replace for the box.
Substitute means going this way, okay? Replace E with an E, or going this way, replace N with an E, okay? In this case, replacing N with an E costs 2, so 1 plus 2 is 3. Or if we go this way, it is 2 plus 1, 3, 2 plus 1, 3. If you get confused, always drop back to this box. Okay. The edit distance between null string and E is 1. Okay, I'm just inserting 1. There is no substitution. Edit distance between I and null string is 1 because I am just deleting 1. Okay, so you understand these two. How about this box? What can I do to match I with an E? I would do this. Okay, I would delete I, then insert E. Okay, this is delete I and insert E, or I would insert E and delete I, or I would directly substitute I with an E. Okay, color always helps. If you can remember what color means. Okay. Go back and let's fill this in. This is going to be 4. How about this one? This is going to be, I think there is nothing interesting will be happening because I don't see any Z's here. 5, 6, 7, and 8. So 8, what is 8? Somebody tell me the meaning of 8 here. 8 is cost of minimum edit distance of the distance between intention and E, right? Yeah. Can I calculate this one directly? No, because I need this number. That's why you need 3 neighbors calculated, then I can do this, right? So let's do this. There is nothing interesting here. Choose the minimum. Okay, come from here. It's 5, 5, and 5. It's 5. Okay. I think if I go up ways all the way, X is okay. It is not interesting. So it is what? Replacement is 2, yeah. Okay, so it is going to be 6, 7, 8, and 9. What is 9? 9 is the edit distance between intention and EX. Okay. How about this? It's going to be, this is going to be 6, 7, 8, 9, 10. Let's look at this place. C, I don't see any C's here. So this is going to be 6, right? 6, 7. Interesting here. It is 5. If I add 1 to it, this is 6, right? Because I am coming from this direction. Okay? So then 7, 8, 9, 10, 11. And for the U, it's going to be here. It is 7, 8, 7, 8, 9, 10, 11, 12. This T is going to be interesting, I guess. This is 8. Substitution, T and T, right? T and T substitution is going to be 7. Then this one, what is this? What should I write here? Well, both of them are 7, right? I need to add one more. It's going to be 8. And this is going to be 9. Substitution again, T. Okay. It could be 9. No, 8, right? Substitution 8. And 9, 10, 11. Okay, let me fill the whole thing. Let's go this way, maybe. So, and there is going to be something interesting at the end. What is this number? Tell me this number. This is 8 from 8. It's like 9 or 7, right? 7. How about this one? 8, 8, 8. All of them 8. How about this one? 9, 9, or because this is n and n, it's going to be 7, right? This is 7. Okay, let's fill this in. T with all of them is going to be 8 and 9. And if I go up that way, it's going to be 8. Is that true? Yeah. Okay. So that's the cost of the distance between int and execution. And let's fill this in quickly. See, to get to this top right corner, I need to fill all the boxes. Okay. There is nothing interesting happening with this E, so this is going to be 9 and
I think we can cut off here.
why?
It would be 8.
It will be, what do you mean? How you mean this top part is 8? Well, maybe, but I didn't see it yet. Let's fill this out and let's discuss about what your observation. So E is, this is 10, right? And this is going to be what? This part is going to be 9, right? Because I am coming from bottom. And this is and okay, maybe something interesting will happen at the end. This is 10, 11, and if I come here, it is going to be 10. Okay, I can come to 10 in both ways, either this substitution or this deletion, right? And then let's go this way, T, and T, nothing is going to happen. It is 9 and 10 and 11. No, is it? Yeah, okay. How about this one? I, okay, replacement, I and I, it is going to be 8, right?
Substitution keep letter.
What?
Substitution keep letter.
Well, substitution doesn't keep the letter, but in this case, the cost of substitution is 0. Cost of substitution here is 0. That's why I chose it. Okay. In this case, the cost of substitution is 2, because E and I are 2 different letters. Okay? Doesn't matter if I come this way or this way or that way. They all end up with 2. In this case, it was different because if I go from bottom, it's going to be 9, 10. If I come from the left, it's going to be 10. But if I substitute it, since substitution in this case is 0, then it's going to be 8. Okay? Now, how about this part is going to be I and O, it is 9. And I and N is going to be 10, right? How about this part? O and I is going to be, what, 9? Is that correct? 9. And how about this one? It is 10. Okay, here, O and O, substitution again, 8. Okay, here it is going to be 9. Here it is going to be 9. When I come here, okay, substitution is free again. It's going to be 8. So this is our final. These are going to be final cost, 8. This algorithm guarantees that you cannot do better than 8. It doesn't guarantee the path, the optimal path, a unique optimal path to 8, but it will tell you that it's going to be 8. So what are we going to do? It says 8. Let's go back, okay? Can I use a different color for this? Because I used black. Is black good? Can you see black? Is black? Is black? Yeah, kind of. So this is 8. I came to this 8 from here, then from here, then from here, then from here, then, well, we can choose either 7, 7, or 6, doesn't matter. I am going to choose this one. Yeah. Then from here, where did I come from? I think I come from here. And here I come from 5, 5, same thing for Then here I come from here and then there. It looks like substitute, substitute, substitute. They are all substitutions, but the last 4 substitutions, they are free. This one is free. Well, this one is, yeah, this one is cost 2. How about this one? This one is E. I think it is, where is E to E? Oh, did I make a mistake in there?
Yes.
This is, yeah, I think these are wrong, right? Let me erase them. Okay, how did I come to this 6? From 5 to, yeah, because this, okay, from 5, yeah. That means what? I inserted one E, right? How did I come to this 5? I think it was this substitution, E to E, right? And then how did I come to this 5? Didn't matter. 4, 4, 3. Let's say I substituted. Then I substituted. Then I deleted. So delete, substitute, substitute, okay, and substitute, insert, then rest of them is substitute. Okay, so that will be the total cost of it is 8. I can find many other ways of coming here, okay? For example, these are all 8, 8, 8s. I come from these 8s, right? Okay. When at this position, I could have branched it this way or that way. They are all the same thing. Either substitute or insert delete, right? They would be the same thing. So this table doesn't tell me which unique path to follow, but tells you I am going to give you many paths, and they will all lead to the minimum edit distance of 8. Choose whatever you want. Okay? Good. So that's called minimum edit distance, and this is the algorithm. That's what you're doing. For any box, when you are deciding on it, you do this. Okay? Choose the minimum of these 3 values. Okay? di minus 1j, which is this one, plus 1. Okay, so 1 plus 1 is 2. Okay, either choose 1 plus 1, which comes from this top part, or this one, 1 plus 1, or this one. Look at the diagonal 0. Add a number to it. It's going to be either 2 or 0. If these 2 letters are different, right? If these 2 letters are different, then add a 2. Otherwise, add a 0. When in our case, these 2 letters are different, so I'm going to add a 2. It's going to be 2. Choose the minimum of it. What is the minimum? This is 2. Okay, this is 2. 2 and 2. Well, they are all the same, so I'm going to put a 2 in there. Okay, and follow the same simple rule until you reach to the top. Okay, edit distance table. Any question? Okay, well, if there are no questions, by the way, this is the table filled in. Okay, it looks like this guy is following this path here. Maybe it is the same path that we followed, right? This is called a non-decreasing cost path. It is not increasing, okay? It is non-decreasing. If you follow this path, your cost is never going to decrease, okay? It may stay the same, but it's not going to decrease. It's a non-decreasing path. And when you realize that after this point is going to stay as 8, how did you decide it? Because you realize that this part and this part is the same, right? Okay. When you come to this one, we calculated everything, but we know that we already solved this problem. We already solved this problem here. Okay. This problem is the problem of matching intent with execute, right? You don't have to solve that problem over and over again. Once it is solved, you keep continuing filling it. You keep filling the rest of the table. That's the benefits of the dynamic programming. One-dimensional problems, sequential problems. You fill in a two-dimensional table like that, and the problem becomes a linear time problem. Okay, the cost is n times m, right? N is the number of letters here, m is there, so it is linear time solution. Okay, if there are no questions, I am going to take some break, 10 minutes. Yoklama nerede arkadaşlar? Yoklama imzalamayan var mı? Yoklama imzalamayan çıkarken imzalasa olur mu? Evet.
Şey anlamadım ben tam olarak. Burada mesela şey var, internete kadar geliyoruz.
Evet.
Intent'i siliyoruz. Sonra mesela geri kalan kısmını ekliyoruz.
Evet.
Ama mesela intentini kadar mesela sildik, orada 11'den 10'a bir düşme oldu. Mesela
Düşme olmuyor. Bak sen onu yanlış anlıyorsun. Bu 10'dan 9'a düşmüyor. 9'dan 9'a geliyor bu. Yani senin fikrin eğer şuraya kadar doldurup, tamam mı? Şuraya kadar interneti ne yaptın? Ta buraya kadar sildin değil mi?
Evet.
Ondan sonra ekleyerek gidiyorsun birer birer. Yani şunun internetinin hızına kadar sildin. E'yi ekledim, X'i ekledim, E'yi ekledim, C'yi ekledim, U'yu ekledim. Ondan sonra 9'a düşmüyor. Bu sana diyor ki bu gidilecek bir yol değil diyor. Eğer buraya kadar gelirsen 10 oldun. Başka yollardan gelirsen 9'luk kos var bir yerde. Burası çıkmaz sokak. Buradan buraya devam etmiyor.
Ha, burada da yani bu şey aslında düşüş değil, bu arada şey oluyor yani.
Hayır burası
Daha kısa
çıkmaz
bir yol
sokak
olduğu
bak.
için
Yani
oluyor işte.
şunun arasında yol yok. Ben buradan geçmedim. Tamam mı? Böyle bir şey yok.
Anladım.
Geçtiysem ya buradan geçtim ya da buradan geçtim.
Ha. Tamam, şimdi çok teşekkür ederim.
Tamam. So when I say it is green, it is yellow, I guess. Blues are blues. How about the reds? Reds are blacks. This is red. And blacks are blacker, yeah. So maybe shouldn't use too much. Too many different colors. Okay, so that's the minimum edit distance, and this is the algorithm. This is the algorithm. This is the algorithm. Okay. What is this? At the beginning, do what? Fill in all the. Somebody complete this sentence. Fill in.
First line and first column.
Yeah, first fill in the first line and first column. Okay, the first row and first column with 0, 1, 2, 3, 4, 5, 9, because you are not doing any substitutions. It is already, these are all deletions. I am eating these letters one by one, and I am inserting them one by one, right? So these are all the stuff. And then after that, we start running this nested loop from 1 to n, okay? From 1 to n. See, these are zeros. Zero, column number 0, row number 0 means it is a null string, okay? And once you do this, at every step, okay, it is an m by n complexity. At every step, I make this 3 comparison. Whichever one is smaller, just choose that one. Oh, this is important. I mean, this number is important because remember at the beginning, what did we say? At the beginning, we said that. Okay, I like to find the edit distance between these two, and between these two, and this, right? I like to find these editing distance between those. And whichever produces the smallest number, I choose that one. That is important. I should do this. But sometimes it is important to know which replacement I am doing, or which substitutions, or which insertions in this case, right? In this case, the edit distance between these two is important, of course, but I like to know where I insert what, or at what position I would substitute. Okay? So for that one, this table is not enough. I need to do something, and I am going to show you that in a few minutes. Okay? That's called backtrace for computing alignments. Okay? So this is what we are going to do. Edit distance isn't sufficient all the time. We need to keep the backtrace of how we made that decision. Okay? When we made that, the final box, we have to go back and follow the path. Okay? So this is basically what you do. You keep where you came from. Okay? You keep where you came from. This guy says that I come to this position from the diagonal, diagonal. And this one says that it doesn't matter where I come, I can come from there or there. Okay? This one says that I come from the left. This one left or diagonal, etc. So if you keep this information, starting from this end, you follow one of those arrows and you'll be fine. So I can do this maybe. Can you see the blue? Yeah, blue. And this one, I am going to, for example, maybe go that way, and that way, and that way, then this way, this, and this, and this, right? I can do that too. Okay? So this is just one way of doing stuff, backtraces. Again, this is a non-decreasing path. See, if I use the green, this is a non-decreasing path too. 0, 1, 2, 3, okay, 4, 5, 6, 7, and 8, 8, 8. Or this one is a non-decreasing path. So you can find many non-decreasing paths. Doesn't matter. Its final cost is going to be 8. Okay? Good. So this is the, again, dynamic program. I mean, edit distance, maybe it is not a perfect NLP application. I didn't use any language information, any linguistic information. It's just the distance between two versus two one-dimensional data. But it's a good start for showing you the benefits of using dynamic programming. Also, we talked about search space tree too. So that was a good beginning. Okay, this is the algorithm. We talked about it. Okay, so every non-decreasing path from 0, 0 to mn is a valid valid solution. It starts from here, then it ends there. And dynamic programming says this: an optimal alignment is composed of optimal sub-alignments. Okay? If we look at this part, okay, from this corner to this corner, there is no better way of going from this corner to this corner. At least, well, at most you can do the same. So if you find a path like this, okay, this green cannot have a lower value than the black one. Okay, so this is optimal path inside this red square, red rectangle. Okay, so it is like this. In Turkey, let's say this is the map of Turkey, right? Okay, if I am going from Kocaeli to Hakkari, and if this is my path, if my path crosses Sivas and Malatya like that, okay, and I know that this is the optimal path between Kocaeli and Hakkari, this has to be the optimal path between Sivas and Malatya, okay, because if there is a better path between Sivas and Malatya like this maybe, then instead of following this green path, I would follow the red path, and the distance between Kocaeli and Hakkari would have been shorter, right? That's the optimality, right? That's the dynamic programming and principle of optimality. Good. Okay. So backtrace with the backtrace, I did this already, and these are the complexities. Time complexity is n times m, the number of letters in the first string, and the number of letters in the second one. Space is n times n. Backtrace is backtracing algorithm, okay? It is only n times m. Can you explain this one? Why is it n times m? Backtrace. After you find this number 8, finding the backtrace is, finding your path from here to the beginning is just n plus m, not n times m. Why?
Because it's linear. I'm following a line, not an area.
Because at every location, okay, you are going to eat either one letter from this one or one letter from this one, right? Sometimes you're going to eat one letter from each. So it's going to be at most n plus m. So it is very, very nice behaving algorithm, space-wise, time-wise, so we use it all the time. I think this dynamic programming was formalized in 1950s by a guy named Bellman, and people started using it in many different areas, and we are going to see at least 4 or 5 different employment of that one. You are taking this course, natural language processing. Maybe you are not doing your research at this area, but I am sure whatever area you are working on, if there is a one-dimensional data, 95% is possible that you can apply this minimum distance in your area. It might be meaningful or not that meaningful, but give it a try and you are going to see that why don't we use this? Why don't we combine this and this and etc.? It will be applicable. Okay, good. There are other concerns, like remember what we said? This is our statistics of people making spelling errors between the letters. Okay, they are confused about between E and A. Instead of E, they are typing A, okay? Here, what else? Instead of I, they are typing E. It looks like they are making mistakes in vowels. Sesli harflerde numara yapıyorlar. Okay? So what is the largest number that you see? I think it is this one, right? 388. Do you see anything larger than that? I don't. And there is another one. Instead of E, they are typing A. Instead of A, they are typing E. Because in English, in most of the words, E and A, they come together, like each, right? Each.
Easy.
Yeah. As that is easy, or A, E. Can you see? Can you give me a word that starts with an A? E? It could be. It doesn't have to be at the beginning of. What? But in that one, okay. Area. What? No, it is this one, right?
Like in air.
Aerial, yeah. Aerial, right? Well, aerial is this like that? Aerial. I don't see it. Aerial. Where is?
Instead of I, there is an E.
Really? This is an E? Okay.
First one.
So as you see, I am confused about between E and I too. Where is I and E? Well, not much, but they are doing it. So in English, they are doing these mistakes. So that means what? Maybe the substitution between A and E is a lower cost, right? Because people are making those mistakes, okay? It is very seldom that people are making this mistake of pressing the button X instead of A, right? It is 0. So it is substitution cost may be higher, right? So how do you do that? I don't know how many. Add up all these numbers. Let's say there are 10,000 keystrokes, okay? It looks like out of 10,000, let's say it is 500, like 0.5% of it, okay, is going to be this one. So substitution of that cost should be 1 over 0.5%. Substitution cost between A and X should be 1 over very small number, right? So it's going to be very high, very large number. That's substitution cost, okay? So that's sometimes we do that. And again, it depends on what you are typing. It depends on if you are typing in English or Turkish. Okay, and sometimes it depends on your subject too, okay? So this algorithm can handle all of them because remember we took the substitution cost as 2. Maybe we can take it as weighted. Okay. So insertion cost, deletion cost, it is not 1 anymore. Remember our algorithm? It used to be 1, 1, or 2 or 0, right? Remember that one? Now it is 1, 1, and some other number. So if these two letters are the same, the substitution cost is 0. Otherwise, there will be a substitution cost. Okay, good. So this is called weighted minimum added distance. As I said before, this guy is 1950s, Bellman. I think he was from Princeton or something like that. They asked him, why did you call this dynamic programming? There is nothing dynamic in it. He said that in order to get funding from the government, he had to come up with a nice name. He just made it up. and people took it, so it is dynamic programming. Okay, good. Sequence alignment in the computational biology. Anybody from the bioengineering department here? No? Well, there used to be some people previously. So they in the bioengineering people, they use these kind of techniques a lot. In fact, they use lots of NLP techniques too. I know some people, they use NLP techniques to scan scientific papers, okay? They parse all the sentences, and they pick some of the sentences they think that they are different from the others, and they run their analysis that way. I mean, for some areas, it is easy to write papers. They kind of automatically write it. Once you have your experimental result, it makes a paper, so they just publish it. So it is like they are publishing it automatically. Sometimes 5 papers a month, so which is, I mean, for a computer scientist, 1 or 2 papers a year is a very big number. For some of those kind of people, 1 or 2 papers a week is not a big deal actually. Well, but if you have those kind of papers available, thousands of papers coming from the same institution, it is not easy to read them. It's like kind of they are producing some kind of a dictionary, some kind of reference. So who's going to read them? So computers read them and they make the analysis. So this is the sequence analysis. This is the sequence alignment between 2 sequences. So where do they use it? Okay, they find the important regions. Let's say they found that this region is common to all the mammals. That's important, right? So they say that this sequence, this subsequence of DNA is common all the mammals. So it must mean something, right? It's what makes mammals different from the other creatures, okay? Or determine their function, or uncover evolutionary forces and etc. Okay? So alignments in 2 fields, okay? In natural language processing, we like these numbers to be small, okay? We like to find the similarity between them, and we use weights and distance. Sometimes in computational biology, they like to maximize their results, find the maximum one, find the similarity between those, and their terms are kind of different, but the idea is the same. See what they do? They start with a very small number, smaller than 0. Instead of adding stuff, they just remove it, right? It is minus t. They are maximizing it, okay? That's what they are doing. So, and these are the. Remember, we multiplied them by 1. Now their distances are different. So algorithm is the same. They are just not starting. You will see lots of negative numbers. That's what I'm saying. Okay, and they in their convention they start their 0, 0 is upper left corner. Okay, not the.
Last page, yes. Before definition D.
Previously we took D1 at the beginning, but it doesn't have to be 1, right? Cost of insertion and deletion. It depends on your area, okay? And these are the weights. Okay, the same thing again, their just format is different. And one important problem they are working on is this, okay? Maybe I don't need to pay attention to what is at the beginning and what is at the end. The important thing is the overlap here. So I can ignore the beginning of one gene sequence, and I can ignore the end of it, okay? Doesn't matter, okay? Both of them, lots of insertions here, lots of deletions there. I like to find the overlapping region. It is either because how they come up with these sequences, or sometimes it is because I like to just find a good enough overlap. Okay. So how do you do this? And in fact, I think we can do the, let's say I have a text. It has, like, this text has, let's say, 2,000 words in it. Another text has 5,000 words in it, or letters in it, okay? And I like to find any significant similarity between these two texts. And let's say these two lines and these two lines are the same or very similar. How do you run the edit distance to find this similarity? Okay, so what are you going to do? If you try to find the edit distance between this and this, it's going to be a very large number, right? It's going to be a very large number. But somehow, if I can find an algorithm that will ignore this part, this part, this part, and this part, then I am fine, right? It's going to find it. So can I do something like that with the edit distance algorithm? Does anybody have any suggestions? The answer is, of course, yes. How do you do that?
Length of the same distance, maybe.
Length of the same distance? Explain it a little bit.
For example, in execution and intention,
Yeah.
the last parts of words are same.
But their last parts are the same. I am talking about in the middle, somewhere in the middle, I don't know where, they are the same. You are going to eliminate the beginnings and endings of the, see, I ignored this part of the match, and I ignored this part of the match. Okay, so both of them. I ignore those blue parts. Can you see the blues? Yeah. I ignore the blue parts, and I am only finding the edit distance between the greens. In this case, if they are exactly the same, then I am going to say, okay, the edit distance between these two lines is 0. Or if there are some changes, okay. This is how they run the cheating algorithms, actually. I mean, if you submit something, authenticate, right? They kind of do the same thing.
Maybe remove insertions and deletions from the end and start.
But I mean, if I run the standard edit distance algorithm between these two, it's going to be a very large number. I don't think that it's going to have a chance to match these two. It's going to make lots of random matches between there and there and there, and because there are so many substitutions in here, right? Yeah.
We can use a threshold, a partial, like if there is under 10% or 20% similarity, we can ignore.
How are you going to do that in this kind of a graph, in this kind of a structure?
I don't know.
Okay, the idea is, yeah, maybe we keep the cost somewhere. I mean, you are saying that I see the cost here, right? If this 8 is getting larger, okay, cut it there. I mean, don't continue in this path. And you are saying that this is not going anywhere. Maybe something like that, but they found a much more compact and smart solution to this. Okay, they do this. What does that mean? The first column and first row are all zeros. So that means what? You can eliminate as many characters as you like from the beginning of those data, or the word. Okay, so instead of starting from this corner, I can start from here or from there, okay? And you are going to look for your solution around here. So that means what? I am doing this, right? Matching some part of X with some part of Y, okay? Overlap detection variant. Or if I like to do it even more, I can do this, right? Anywhere in the graph, okay? Anywhere in the graph. Like you said, keep some kind of a threshold. This guy Smith Waterman says, keep some kind of a threshold and try to find these kind of low-cost, non-decreasing values. Okay? Maybe this makes a good homework, right? Maybe your first homework should be this one. Yeah. Okay. So again, well, this is not much of a natural language processing problem, because I mean we are comparing letters to letters, but it becomes very interesting. Instead of comparing letters, let's compare words. Okay. Remember how we compare the words? It said states or indicates. They are very similar words in terms of meaning. So the substitution cost between those two is similar, right? So that's how if I write something like that, Sabah evden gelen adam, on Google, it's going to tell me that I couldn't find anything like that. Nobody said something like this on the digital earth. But if I do this, adam sabah evden, so it kind of finds these and it says that I couldn't find it, but if I insert some stuff in it, and if I remove some stuff in it, I can find some kind of a match. Of course, they are not running exactly the same thing. And it doesn't have to be always, for example, instead of adam, maybe it could be kadın, right? Do I have anything? Adam. Instead of sabah, maybe it is sometimes akşam, because they are meaning-wise. See? Just insert some words and coming back together. So we are interested in these kind of stuff in NLP. You don't have to match the exact words, but meaning-wise similar words. If you are doing that, then you are doing something more related to natural language processing. It becomes a typical artificial intelligence problem. Edit distance is not an artificial intelligence problem, because we know its final results. We know the optimal match between two strings, right? To make a problem artificial intelligence, to give a problem artificial intelligence aspects, you most of the time don't know the exact answer, okay? You say this is good enough, remember those? So I typed sabah evden çıkan adam, and it's giving me a bunch of results. None of them perfectly matches. And when I typed it, I knew that. I knew that this is such a rare occurrence of Turkish clump of words. But I know that it's going to give me related stuff. Okay? So the results were, for me, they were successful. Okay? So if we implement all this stuff, we are not doing NLP, especially AI aspects of NLP, but we are implementing some useful tool for our NLP applications. Okay, so when I said maybe this would have been a good, homework, I meant let's match the words, and if the words have the similar meaning, then we'll be fine. How do you find the similar meanings of words? How do you know that adam and kadın, they have similar meanings, especially their part of speech is the same. They are both nouns, and they both refer to human beings, right? And they are usually used together. How would you find that? Hint, I am going to give you a dictionary too. I am going to give you the Türk Dil Kurumu dictionary. You look up both of those words, right? And if their definition are similar, and if their definition include each other, you know the synonym dictionaries, terazüsüz, like this one. In Turkish we don't have it, maybe. Yeah. So when you say, okay, when you say man, okay, in this one, there were, okay. Yeah, antonyms. So it's going to be just the opposite of it, or how many women are there? One is here, the other one, where did it go? Yeah, well, under the adult, I have these, okay? So if you find such a resource, find these two words and try to see if they are similar, or try to see if they are at least related, okay? I bet when I look for the word man in that dictionary, I bet I cannot find any word like desk, okay? Desk and man, they are both nouns, yeah, that's true, but I don't think that you are going to find desk in anywhere, either in the antonyms or the synonyms or the other kind of related words, okay? So again, no exact solution to this problem, but you can do some intelligent stuff. You will say that I am not sure if this is the perfect results, but I think I am doing as good as Google in this case. Then that's an artificial intelligence stuff. Good. So let's move on. This local alignment example, okay, am I going to find, for example, this ATC with this ATC? See, these are all filled with zeros. So once I found it, see there are, this one is okay, and this one is okay too, 3 and 3. Okay? This one solves this problem here, ATC, and this ATC. And this one is where? This 3 is, well, yeah, well, it is solving way bigger problem here. Their costs are 3. So it is up to you which one you would choose. Okay, so that's it about the minimum distance. Any questions? Okay, good. Since you asked lots of questions, your first homework will be about finding the minimum edit distance between, or finding the similarity between two very long text, but you are going to match words, not letters. Good. So let's continue our discussion with morphology now. Okay. In morphology, one of the techniques that we use most often is the finite state methods. And today I am going to look at it. I don't think that I will have time to, maybe I shouldn't clear it, to finish up everything. But, well, what's going on? I am supposed to finish this lecture by 16:20, right? If I give you 10 minutes of break, should I give you 10 minutes of break? Or continue? Break? You want break? Okay, then let's take 10 minutes of break, and when we come back, I'm gonna do half an hour of more lecture. Then we will go. You will go home. I will stay here.
konuşmayla kaydediyor.
Yani konuştuk. Tamam yazmadan yaptım.
Ona göre sıralıyor değil mi?
Okay, many of you already know about the finite state methods, but for those of you who are not that familiar with these methods, I will make an overview today, maybe next week too. Okay, we already know regular expressions. When you, for example, use your regular Unix prompt, when you say stuff like ls star means everything, right? Or ls a question mark and a question mark. Can I do this? I can, but I didn't find anything. Question mark means that just a single occurrence of anything, just one thing. Okay. What other stuff? A star, yeah. I need an A at the beginning. I don't care whatever you have a rest, okay? So I don't have anything that starts with an A, right? No such file on directory. I don't know.
Minus A.
What?
Minus A star. Maybe. That will work.
What do you mean minus A? What is minus A?
S minus A star. That will work maybe.
No, I don't have anything that starts with an A. If I have this, okay, I think I have many stuff in there that starts with an A. So I just saw it. Everybody does it. Emacs uses it. VI uses it. Our regular Bash shell uses it. Regular expressions are everywhere, and they are very useful. So why don't we use this for the analysis of morphology? That was the idea. But we are not going to stop just there. We will be using more than the regular expressions. We will be using more. You know this, right? I mean, I think this comes from VI. This one says that find all the instances of the word in a text, okay, the. But this one only will find the lowercase the and nothing else. And to make this find for both that starts with a lowercase and the uppercase letter the, okay, then you do this. But this will match this word right there, because there is a there. Then maybe I can do this, a white space, then another white space, okay. In that case, it's going to match whatever we want. So we used a regular expression to find all the occurrences of the. For a regular editor, this one and this one are two different things. Or this one, these three letters, and this one, these three are the same thing. For our natural processing purposes, natural language processing purposes, these are the same, these are different things. That's what we are trying to achieve here. Again, we started very simple, but we are going to see it later. Okay, and by the way, when we do that, okay, we run into problems like I don't want to match there, then, and other. These are false positives, okay, and if I don't match this the that starts with a capital letter, then that's an error too. Okay, that's a false negative. Anything false we don't like. Okay, anything false that we don't like. Anything true we like. For example, let's make this box. On the table, I like to match this. This is okay. True positive. Okay. This is a true positive. And let me find another one. There is one. If I didn't match this, and this is a true negative, and I like this too. Okay, this is a true negative. And let's say these are positives and these are negatives. Okay. Oh, okay, sorry. Okay, this is a true positive and false positive. Let's make a false positive. Okay, false positive on 1 bigger than, no, this is not, if A less than B, then, so this is a false positive. I don't like this the to be found, and there will be a true negative. Okay, this is a false negative, and this is not correct. False negative. I didn't find this. The man. If I didn't find this, this is going to be a false negative, and I don't like this. I don't like this. All the falses I don't like, and one final one, true negative. If I didn't find this, there is nothing. Okay, and I didn't find this in there, then it's going to be true negative. Okay, so I like these two boxes. I like these two boxes, true positives and true negatives, but I don't like these false positives and false negatives. Okay, so this problem will come a lot. Those of you who took data mining or machine learning courses, they will know this table, of course. But for those of you who didn't take it, so we do this kind of a classification. Okay, we don't like false positives or false negatives. We like true positives and true negatives. Okay, and usually we try to keep these two numbers up.
False, true, or false computer response, positive or negative reality.
No. True and false in our world. Okay, true and false, they are related to our world. Positive and negative, that's what computer says. Computer says this is the that you are looking for. This is not the that you are looking for. Okay, so both of them, computer says it is I am positive this is a the. It says that I am positive this is not a the. Okay, computer says negative and it is true. Computer says positive, it is true. Computer says positive, this is a the, but it is false. Computer says negative, this is not a the, but it is false. False and true are for humans, for us. Positive and negative are for the computer. Okay, good. That's a good way of looking at it. Yeah.
Why is then false but there is true?
What?
You put there in the table to a negative, but then to the false positive.
Now, suppose I run this expression. Okay, it said that this is the that you are looking for. I found it. Okay, then I'm saying it's fine. Suppose my computer program said that there is a the, but I don't like this. This is not the that you are looking for. Okay, so it gave me a negative, and I said it is okay. In this case, if it says it is positive, then I would say it's false. So the computer says it is positive. Okay, for this one and this one. It says negative for these two. So in this case, computer is right. In this case, computer is not right.
I don't understand because true, negative there. Computer should say true, positive.
True, negative, yeah. The computer should say, I am not seeing any this, the keyword the in there, right? That's what the computer says. Well, this is not a maybe good example, but what kind of example?
Definition the
Yeah.
after.
Yeah, my task is find the determiner article the in a sentence. The computer says that, okay, I found that the in here, which is true. I didn't find any the here, which is true too. It's a negative, but true. The computer in the bottom case says that, okay, I found a the in here, but it is wrong. It says I didn't find any the's in there, but it is wrong. Okay. So for this part, the computer says I found it.
Okay.
For this part, computer says I didn't find it.
But I don't understand because there is anything true.
I am not telling you. I am not telling you what kind of algorithm I run. Okay. I am just saying that. Let's say I have a function. Okay, good. Let me do this. Let's say I have a function. Function name is f1. I give the string to the computer on the table. Okay. The computer is going to give me a true or false. Okay. On the table it says true. There is a the in here. The same function, I said there is nothing. Okay. The computer said false.
Why false? I don't understand.
Well, I didn't write this function yet. I didn't tell you what the function is. Okay. I am trying to measure the performance of this function f1.
Because then 4 letter 3.
Are you listening to me? I don't know what is inside function f1. I don't know. F1'in içerisinde ne olduğunu bilmiyorum. Sana söylemedim bile ben onu. Okay? So, f1 is such a function that it returns true for this sentence, it returns a false for this sentence, and it returns a if a less than b, then it returns a true for this one, and for the final one, the man, it returns a false. Okay. So this one is a true positive. Whatever this function f1 is, I don't know what it is. And this one, there is nothing false, and this is a true negative. Okay. This one is if a less than b, then this is a false positive, and the man returns false, and this is a false negative.
For example, sir, if algorithm is looking for small letters,
Yeah.
and there is nothing also starts with a capital letter.
Well, in that case, it's going to not. Well, yeah, you are trying to find an f1 such that it does that. Yeah. Well, I didn't want to run into that one because if I do that, one of the boxes will be empty, so I didn't want to do that. Okay. So if we have such a function f1, if it behaves this way, I don't know how that f1 works. My table would be this. My table would be this. That's what I'm trying to say. Okay, so these are type 1 and type 2 errors. Type 1s are false positives and type 2s are false negatives. Okay, actually most of the time I don't care which one is which. Okay. So let's say I have a function f1. This function returns a Boolean. Okay, let's look at this function. A C function Boolean f, let's say 2. It takes a string s, and the function implementation is return true. That's it. Whatever you give this function, it always says true. Okay, so if I look at the false positive, true positive table of this function, okay, remember this is positive, negative, true, and false. Okay. So at the true positives box, let's say I ask lots of questions to this one. It gave me a bunch of numbers. Okay, it gives me a bunch of results back. It always says everything is true. Okay, whatever I give it to this one. So half of the results will be in this box, true positives. half of them will be false positive, but it is not going to say anything inside this box, true negatives and false negatives, because it never says anything about the negativeness, right? So this is such a function F2, very stupid function. It doesn't even look at what is inside S. It just behaves that way. So it fills everything in these two boxes and it ignores these two boxes. Okay? So such a thing can happen, and in fact we are going to see examples of those. So that, I mean, only this number being high, okay, let's say I asked 100 questions, it said 50 of them are true positives and 50 of them are false positives, okay? So you cannot say, well, 50% of the time it is doing good. No, I don't expect it, okay? 50% of the time it is doing good is not a good thing, because 50% of the time it is doing bad. This is doing random decision, actually. Okay, so yeah.
Türkçe sorsam sorun olur mu?
No. Okay, okay, ask me in Turkish.
Şimdi bu az önce anlattığımız F fonksiyonu var ya F1.
Evet.
Orada mesela F'in nasıl çıktı vereceğini biz kural olarak koymuş muyduk?
Hayır, yok, F'in ne olduğunu söylemedin diye ya ben sana. I don't know how F1 works dedim bak.
Peki bunun çıktısını nasıl veriyor peki? Yani true false olmasını rastgele mi?
F1 mi?
Hı hı.
Nasıl olduğunu bilmiyorum dedim ya F1'in. F1'in içerisinde ne var yok bilmiyorum. F1 böyle bir fonksiyon olsun, bunları versin. Eğer bunları veriyorsa böyle bir tablo oluşur diyorum ben. Bir tane F2 yazdım. F2 eğer bunu yapıyorsa şunlar dolu olacak, bunlar boş olacak. İyi bir fonksiyon değil bu. Hiçbir şeye bakmıyor bile F1'in içerisinde. Okay, let's look at this one then. Okay, okay. Let's say, okay, let's say, okay, while you are asking it, let's look at this one. This one, let's say our function is f1, and it is searching for this the, okay? So this one, let's draw our table again. Let's draw our table again. Okay, this is true, this is false. Okay, no, this is positive and negative, true and false. Okay, let's say our function f is doing this. It is looking for this the, okay, the in a sentence. For a true positive thing, this is going to be fine. The man. The man is true positive, because if I feed the man to this regular expression, it's going to find the result. So this is true positive. Okay, so let's look at the true negative. A book. Inside the string a book, this is not going to find this occurrence of the, it's going to be true negative. Let's look at one false positive. There is, okay? So in there is, okay, it's going to find a the, but actually there is no the in there, right? And give me an example for false negative.
A book actually false negative.
A book is true negative. Okay? So give me an example for the false negative.
There is false positive değil mi?
There is false positive, yeah.
Ama sadece the'ye bakıyoruz ya, boşluk olmadığını da kabul etmesi.
But my task is find the instances of the word the in a text as an article the. Okay? I don't see any articles in the in there. There is a there is different than the.
Isn't it the third one?
What?
No, on the left.
Yeah, maybe if I say the book, okay, there is a the in the string, but this one is not going to find it. Okay, now you know, okay. Let me write this down then. Boolean f is going to take a string s, okay, and it will return. How am I going to find it? Okay, return S contains the. Okay, if this is the function, it will behave this way. And I like this one. It works here, it works here. Doesn't work here, then doesn't work there. Okay? But maybe I should have started with this example. But the point I am trying to make is we like, okay, we like trues. Trues are good, okay? True positives or true negatives. We don't like falses, okay? If I ask 100 questions to this f function, I like all these numbers to come into this one or that one, either true positives or true negatives. I don't like these two boxes. Okay? Good. Okay. I already kind of talked about it, not much, okay? So we are going to use finite state automata, whatever it is. I'm going to give you the example in a few minutes, okay? We are going to use finite state automata to make decisions about the morphological analysis of the words, okay? I am going to ask questions like, is masalı analyze that there is a masal as the root of the word, and is the accusative norm of the word. Accusative i hali, dative e hali, possessiveness iyilik eki. Tamam. That's the corresponding Turkish terminology for this one. Okay, so this is the accusative masal and accusative masalı. So I am asking the same question, okay? Is this the morphological analysis, correct morphological analysis of this word masalı? If I am getting it true, then I am doing this right, okay? How am I gonna implement such a function? In this case, I have implemented the stupid function like this using my string library, C++, C or Java, string library, whatever it is, okay? Can I write such a function to give me this? Masal is the noun and root of it, plus there is an accusative suffix to it, okay? That's what we are going to do with the finite state automata, okay? I'm going to run this finite state automata. It's going to give me one final result at the end. It's going to either reject it or it's going to accept it. There is very simple finite automata. Let's start with this one. Let's say I have a finite state automata that recognizes sheep language. Kuzu dilini tanıyor. Okay? So how many words are there in the sheep language? Well, there are many words, but they are very similar. Grammar-wise, it is very easy to write. Okay, sheep words. Okay, let me write one. This is a sheep word. Okay, it says that anything that starts with a B, and if anything that has at least two A's that ends with an exclamation mark is a sheep word. This is a sheep word. Another sheep word is this one. Another sheep word is, okay, this one. But this one is not a sheep word. This one is not. This one is, and this one is. So how am I going to write a function that will say these are all recognized sheep words, but this is not? The answer is, in this case, this regular expression. Okay, it says that always start with an B and A and another A, at least one A. Then you can have as many A's you like. but at the end I should have an exclamation mark. That's a regular expression, and this is the corresponding finite state machine. Okay? So you might think that, well, I mean, Turkish is a little bit more complicated than this, and you are right, but we are just starting to look at the problem in a very simple way. Okay? Remember I showed you what I showed you about this Turkish morphological analyzer, Çöltekin morphology. I think I showed you this last time, right? Where is it? Just play with this, try to understand it. Let's write masalı. Okay, and analyze it. There are many analyses of it. Okay, the masal noun is the root word, and there is a...
Sir, what's the name of the website?
What?
You can't see the name of the website. What is the name of the website?
I don't know. I just type in Google Çöltekin and morphology. It comes. I think it is Çöltekin net. Well, just watch the video. Okay, it is on YouTube. By the way, last time I showed you that movie, I get a strike from YouTube. Remember the movie that I showed you? Space Odyssey. It says that you are copyright infringing somebody. So I have to clip that out. Okay, this is P3 as third masalı third. This is plural and third singular. Onların masalı. But this is this single? Is it third person singular? Yeah, onun masalı. Third person singular, and this is the accusative, and this is masa. See, this is adjective. Li suffix that makes a noun adjective, right? Masalı ev, etc. Okay. So what I'm saying is that all of these results, they come from a finite state automata like this. Okay. A finite state automata like this, and we are going to see how it happens. Okay. By the way, as I said, this is a very ambiguous, This is a very ambiguous word, a Turkish word, but most of the Turkish words are like this. Let me see what masa returns. Masa, right? Noun, okay, masalamak. This is okay. It says that you can make any word, any nouns, a verb without doing anything in Turkish. Something like that. And this is if I make it a verb, then it's like for the third person or the third plural person, you are kind of giving an order imperative word. Okay, so even that one is ambiguous without any suffixes. This doesn't happen for languages like English or something like that. But again, even such a complicated language like Turkish can be handled using this kind of a tool, finite state machines. Okay, and this is just for the introduction of it. But it looks like I'm out of time. Next time we are going to continue from this point on, and I am going to show you examples. Well, as you see, these are all cheap language stuff. Can I have, well, I don't think that I will show you complicated Turkish or no. Let me show you, okay, don't go anywhere. I think I should give you this, paper of Turkish morphology parser from, I guess, from 1990s. These are all techniques, Kemal of Lazer. And this is, okay, standard stuff. I'm going to show you a few. See, these are some of the regular expression rules. I think at the end, he gives the finite state machine. Yeah, okay, good. You start from here, okay, by adding these words. These are lık, cı, cık. The capital H is either E or I. Okay, I ya da I. Şu da E ya da A, onlarla ilgili tanımlar falan filan var. Bir kelimenin alabileceği formlar bunlar. Ne diyor? For nominal morphotactics bunu vermiş. Diğerleri devam ediyor. Tüm Türkçe için morfoloji kuralları burada tanımlanma. You take this and you implement it, okay, in a finite state machine and you are done. Okay? This is available. And this is all available to you, and many people have implemented this, and one of them is that Çöltekin morphological parser, very simple. And in fact, once you have these rules, you don't have to code anything. You don't have to code anything. There are tools that convert your finite state machine to convert finite state machine to executable systems like those. By the way, in those days, Osmanlılaştıramayabileceklerimizdenmişçesine. I think this was the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12, 13 suffixes, different suffixes. If you take all these combinations, they say that on the average there are 5,000 different forms of a Turkish word. That's why it is very difficult to. How do you match two words if they are going to take this kind of morphological forms? Okay, it's difficult. Finding the text similarities in Turkish is not easy because the words can take different forms. Osmanlılaşmış, Osmanlılaşacak, Osmanlılaştırılmış. These are all the same word. How do you match these, right? So you need to do the morphological analysis, maybe just match the root of the word or do some other stuff. Again, this is related to your first homework. Okay, good. Any questions? So read this paper. 2-level description of Turkish morphology. You don't have to understand all the technical details of it. Just try to understand what's going on. Okay, very, very old paper. Before the internet. See, this is not an internet address. This is a bitnet address. 1990s, as I said. Okay, what is the date? Well, I don't have the date. I think it is 1990s. Okay, good. I'll see you tomorrow. No, not tomorrow. Some of you tomorrow, some of you next week. Most of you next week.